Hey everyone, so this is going to be the video for lab 3. So, in this lab we're going to be making a binary counter, and you're going to need to do some other stuff too, but let's just get in it now. Oh yeah, in all the previous videos the recording settings didn't have the mouse enabled, but now you can see my mouse. Whenever I click, it just shows. So I hope that makes it better. Okay, but just put the lab. Okay, so this is our lab counter. It's going to be you're going to be making an 8-bit counter. Then, oh yeah, these are the specifications. You're going to need to make a count up and down. You're going to be able to load in a manual value and yeah. This example here is going to be very similar to in the lab. Instead of it being an 8-bit counter, this is going to be a 2-bit counter. So, just a refresher on binary numbers. Let's say we want to count to 1, 2, 3, 4. The binary representation is going to be, oh, so we want to count to 0, 1, 2, 3. Yeah, that's better. Want to count to 0, then 1, then 2, then 3. Well, 0 is going to be this, 1 is going to be this, 2 is going to be this, 3. And the number of bits is going to be log base 2 to the highest thing you're counting to. So that's going to be equal to, get my calculator real quick. Okay, so log base 2 of 3 0.5849. Okay, so that means what the rule actually is round it up. Number of bits is equal to the highest number you want to count to, log base 2 of it rounded up. So you want to count to 0, 1, 2, 3, 4, 5. Log base 2 of 5 is equal to 2.32, but we round up. So it actually turns to 3. And what do you know? In order to represent 5, you need 3 bits. So that's how you know how many bits you need. And hence how many states. Okay. So now that you know that, yeah. So each bit is going to be represented by a state, which is what this table is. So for bit 1, actually this should be, I kind of want to reverse it, but I don't know. Okay. For bit 1, it's going to be 0, 1, 0, 1. For bit 0, it's 0, 0, 1, 1. And oh, well, I guess there's one other trick I should show you guys. For numbers in binary, like let's say we have 5. That's going to be 101. You might be thinking, well, how do you know? The way you do it is this. The check is going to be, you see how this is number 0? Place 1, 2, it's going to be equal to 2, 2 plus, wait a minute, 2 to the 0, yeah. Where this goes there and this goes there. Now let's do a more random one, like 13. And the check for that, this place 0, 1, 2, 3, 2, plus 2, plus 2, 3, 2, 0, 2 to the 3, plus 8, plus 4, plus 1 is 13. So that's how you know that. And yeah. Okay, so this is our state table. Whenever we're in the first state, which is 0, 0, we want the next state. Yeah, when we're in state 0, 0, we want our next state to be 0, 1. And then when we're in 0, 1, we want the next thing to be 1, 0, or 2. And when we're in 2, we want to go to 3. And when we're in 3, we want to go all the way back down to 0. So it can loop over and over again. If you guys have any questions. Yes, maybe what these are. If you don't know what's being used to store these, it's being stored in registers. So you're gonna have a register storing each state. Okay, it's reconnected now. So yeah, it's gonna be stored in registers. So this will be like the B01, this will be B11, and this right here, this would be when these registers have this value. And then this one right here is going to be when the registers have this value. And then it keeps going like that. So let me just write it all out. So it's going to have 0, 0, 0, 1, 1, 1, 0, 1, 1, all the way back. And it's going to keep cycling through that over and over. And And then you might be wondering where, well, where does this play? It's going to be right here. So this is the next state. Actually, what was I going to say? Okay, never mind. Let's delete that real quick. Okay, so now that we have our state table for a 2-bit binary counter, we're going to make K-maps for the next state. So, and because there's two outputs for the 2 bits, we only need 2 K-maps. And also this entire K-map, this entire truth table can be represented in terms of like this. Or, oh, hold on. Zero row, 1, 2, and 3. And these numbers correlate to the binary value right here. So M0 is 0, 0, 1 is 1, M2 is 2, M3 is 3. Let me just write that near. Yeah, so this correlates here. And minterm representation is this one. Um, so all of the rows that have a 1, oh, and this is for B plus 1. Okay, so for this row, the ones that have a 1 as the output are going to be put in the minterm. So we can see M0, that goes there, and then M2. And then the max term is just the opposite, so all those with 0, so 1 and then 3. So if he gives you like this notation, you can know to change this to be in table form. Okay. So once you make your K-maps, yeah, so then you're gonna make your K-maps. So because it's a two-dimensional thing, you're gonna have B0 and B1 because your inputs go here and here. And then 0, 1, 0, 1. And this one, when both are 0, 0, 0, we get 0. When B0 is 0, so this one, and then B1 is 1, the output is 1, so 1. And then when B0 is 1, so here, here, and B1 is 0, so here, we get 1. And then when they're both 0, it's 0. And then when you do the same thing for this one, you get this one. So then you get these two equations for the next state of B0 and of B 1 plus. And then when you realize it, it's going to be like this. Or actually, no, it's start from the beginning. Yeah, it's all worked out already, but it would be better if we just go through it completely so you can understand. Okay, so every time you do it like this, just nice and simple, with a state and a next state, it's implied that you're going to be using D flip-flops, which is like this. This is a D flip-flop. Oh, there's different kinds of flip-flops that you can use. Some of them are more complex than others, but the D is the most simple of them all. So, we need two flip-flops. For each thing, this will be the zero. Shit. So this top flip-flop is for B0, and this bottom is for B1. And then you might be thinking, well, where does the B0 plus go? Well, that's going to be here. And then the B1 plus goes here. So then using the equations, we're going to have an OR gate, two AND gates, zero, B1 prime, zero prime, there. So this whole thing correlates to this. And then B1, just B1 prime. Or what you can do, another way of visualizing it, is just B1 going through an inverter. But it's the same thing. Just use the condensed notation. And then the important thing is to know that this loops around. Let me just draw it better. So you have two inputs, B0, B1. Okay, so for this first AND gate right here, we got B0 and B1 prime. So we got B0. Then we got B1 prime. So it's B1 here, and then it's B1 prime after the inverter, and this is B0. So then we get these two ANDed together for there. And then for the next one, it's just these. Oh. So yeah, and then it's going to be B0 prime going in there. So this AND gate corresponds to this one, and this one. It's going to be B1 inverted going in there. Okay, and now let's make it loop around properly. So if we simulate this entire thing, it should work. So let's do that now. The flip-flops, we need 2 of them. Alright, let me bring this up. We're gonna need gates. And then we're gonna need an inverter. 2 inverters. So then this is gonna be our B0. It's gonna be our B1. And then according to this, oh, what am I doing? Yeah, our B0. Yeah, B0 goes in there into the first one uninverted. And then B1 goes in there inverted. So we just built that one. Now this next one, B0 goes in inverted. And B1 goes in uninverted. And then for this bottom one, B1 goes in inverted. Fuck. What do you know? It's doing it exactly how we wanted in our truth table. Starts up 0, 0, and then 0, 1, and then 1, 0, and then 0, 1, 1, and then 0, 0. And it repeats over and over again. So what your guys' lab is essentially to repeat this entire, well, that's the thing. This video is going over all of the complex theory involved with how this works. But the code that Dr. Morton will give you, a lot of the nitty-gritty details are going to be already done. So you won't need to do all this, but you could if you wanted to. It is much harder to do it this way, but this video is intended to just give you guys a complete understanding as to how a binary counter works. Like, this is the gate level logic that is needed to make a binary counter. So if you want to do it, but have it being 8-bit or 3-bit, be 0, 0, 0, 0, 1. Hold on. Red is better. If you want to make it count through all of that, and the state table will be like this. You pretty much just have state B0, B1, B2, B2 plus, B1 plus, B0 plus, and then you make key maps, 3 of them. Key map number 1, B2 plus, and then for B1 plus, you would have this general shape, and then one last one for B0 plus, and then Yeah, then the stuff that goes in here and here, that was all covered in the last video. So yeah, this right here is a lot more relevant. Oh, let me move it over. Okay, now you can see it. So all of this right here is a lot more relevant for this lab that you're doing because this is how you would actually build the 8-bit counter instead of it just being a 2-bit one. And you would just make the K-maps and get your equations, and then you can use the simulator that's right here to simulate it, but you have to do it in Vivado. And yeah, let's simulate this one right here in Vivado. Or not simulate, but actually make it. We don't do simulations that much. Okay, so you're going to create a project. Next. This doesn't matter, so let's just put it wherever you want. Our TL project. Create a file. Just do NF for normal file, because this is where we write all of our code in. DF constraint file. Okay, this is the most important part. Family arc7 CSG324, and then you pick that bottom one there. Wait a minute. Yeah, that one. Yeah, that's the one you're gonna pick. Yeah, finish. Okay. So got these two equations. Let me get my board. Oh yeah, so this right here, this is a prime example of something really advanced that you guys would be doing in the future. Today, at Southwest Research Institute, I had to use the board, the very same board we're using in this class, to make an analog to digital converter. And that was kind of complex. But probably at the end of the semester, I'll teach you guys how to do that. Get that back up. What am I doing? Gotta reconnect. That's how I do it. And then I press that. Okay, there we go. Okay. Jewel. We're gonna have a clock. And the reason why we have a clock is because it's a sequential circuit. That's this thing right here. Oh, and then also, yeah, on the little diagram we made, the clock would go in there. Clock. And then we're gonna have LEDs. So the clock is always an input, and then the LED is gonna be the output. Or try and guess what goes here. It's 1, 0 LED because we're making an array of LEDs. So, and then we're going to need to define an internal register. Reg, call it reg, hold on. We're gonna make an always block. Postage, CLC, begin, end. Okay. Oh, and then we're going to define this as 1 tick B0. And then equals x plus 1. I'm gonna assign LED to x. So yeah, what's gonna happen is we're gonna start off with x having, oh, what am I doing? 2 bits. So it's gonna be 0, 0, then 0, 0, 1, and then 1, 0, and then 1, 1, and then it'll repeat. Because that's what it's gonna do. It's gonna start off at 0, 0, add 1, and then yeah. Okay. So now that we got that, put the constraint file in. With the lights. Hold on, look. I think it's better with the lights on. Okay, so constraint file. Okay. So, okay, so then we're going to change this to be CLC because that's what we named it here. The LEDs Only need 2. There we go, it's already named perfectly. Because there's going to be 2. One for 0 and one for 1. If for some reason we did it like this, and we wanted to use that third one, then we would have to uncomment these 2. But we're not doing that. Shift that back. So then let's run simulation. I mean, what am I doing? Generate bitstream. It was like a live session, so it can be more interactive. I don't know, maybe we'll do a live session once the semester starts. So now that that's good, we're gonna go to the hardware manager, open target, auto connect. Thing is if you go to settings here and then click this, if you did it wrong the first time, you can always edit it here by clicking this one again. It's just that I guess last video with the mouse not showing, that would have been hard to see. So take note of that. That's important. I'll can program the device and how it works. Ah, this right here. It's a good thing this happened. See how it's just stuck there? It's just the 2 LEDs on. It's just not counting. The reason for that is because the clock is too fast. It's using the 100 megahertz clock. So what we need to do is make a clock divider. Get one? This is a clock divider. And you do not need to worry about how this works. The clock divider is something that only needs to be written once, and you never ever have to write again. You just cut and paste that there. And then the top part, this. Minimize that. Then we have to put this into our main module. And then we want to use CLC slow, because we want it to be slow. And the reason why it's slow is because of the parameter. With 2 correlates to CLC multi, which is something we'll use later. And then so you'll see slow correlates to width 1. So the more zeros you add to make it bigger, the slower the clock will be. Okay, so then when you use that, it should be visible now. Good. Turn on my fan real quick. I guess I can talk about some theory. Well, oh, never mind. Just started. Okay, let's see if this works. Oh, yeah, okay. Lights gonna help. So as you can see, it's going through all the states, counting up in binary. 1, 2, 3, and then back to 0. And it repeats again and again. But now let's say we want to add an enable, because in your lab, there's going to be an enable, parallel load, a counting up and a counting down feature that you need to add. And your lab is, even though we're going to go through a lot of it here, this is being done using very different methodology, much more complex methodology. So if you want to really hug the video content, you could redo the entire lab using just all of this knowledge here. But that would not be recommended, because if you have a good intuition as to what goes on, you're going to be able to finish the lab in 30 minutes. Okay. Okay, let me pull up my thing real quick. Right here. Oh, now I gotta reconnect. Okay. So, okay. So let's say we want to have an enable switch. Right now, with how it is the clock goes in there, and the clock, these outputs only change when a clock pulse comes. If there's no clock, these values will be fixed no matter what. So if we want to have it be frozen until a button gets pressed, what we're going to do, we're going to put an AND gate, and then what are we going to put here? We're going to put our button, and then that is what we will use. Because the clock will be going ones and zeros, ones and zeros, ones and zeros. But only if the button is high, because if it's one and then the clock pulse is one, you only get that one coming through if they're both happening. So yeah, that'll be an enable. So let's go make that in Vivado now. We're going to have a new input. We'll call it EN for enable. So let's try. Alright, I'm going to try my best to just do it exactly like this with an AND gate going into the clock. Oh wait, hold on. We can use this real quick. This is a very good simulator. Okay, so our button. Okay, so you see how the clock is ticking? But because it's an AND gate, this is 1, yeah. But because this is always 0, you're not going to get any change here, so it'll always be 0. But if I hold the button down, it lets there be a change. So you can see that it's like an enable. It enables the whole process to start. It's like a start button. But when I let go, it stops working. So that does work. So let's go make that now. Um, hmm, hmm. How could I do this? I think you would do if yen. I don't want to get too similar to what you guys are going to be doing in the lab. Let me try and do it exactly with an AND gate. Wire, wire XQ, just two random digits. I mean, letters. Almost said two random letters, yeah. Almost said something stupid. These things called primitives in Verilog. Hold on, I'm gonna pull up something. Forgot I'm on camera. Um, okay, yeah, I see. So this basic structure is the output, and it comes first and then the inputs. Okay. So we're going to XQ to be our output, and then you'll see slow, and then EN. Then we need to change this. What do you think this is going to be? It's going to be XQ now, because if you go back to the simulation, this becomes the thing that changes. This is our XQ, this is our CLC slow, this is our B enable. What's going on? I don't know. Something happened. I don't know, and I don't care. It worked last time, I think. But yeah, should work. I do. Good stream. Okay. Okay, let me program the device. Oh, what am I doing? I gotta go in here. I didn't. Okay, so this is going to be EN. Okay, now we want to generate the bit stream. I'm going to map it to a physical thing with a constraints file. I'm going to have a load in there. Oh, reconnect. Okay. So you might be asking yourself, what is the load feature? Hold on, did this load? No. Okay, so you might be asking yourself, what is the load feature? So before, B0 and B1 would just kind of increment, but what if we wanted to manually set those values? what we would need to do is add a load. So we need to get more flip-flops. Plus A, the thing we want to set. Oh, but oh, and then this right here, so B0 output read in. Bit B. Maybe thinking, well, if we just attach CLC, it's just gonna force everything to be A and then B, like all the time. But we don't want it to happen all the time. We want it to happen when a certain button is pressed. So we AND load button. Okay, I'll generate that later. Let's get back to our simulation here.